everyone. My goal today is to speak very briefly a bit about how to create DPF workflows with PyDPF core, because the main point of using PyDPF core to interact with DPF is the fact that you can create operators and build workflows with it. Otherwise, you have other dedicated libraries which are more simple to use. So yeah, I just wanted to give a brief overview of how to build workflows. So just to go back to basics, an operator in the DPF ecosystem is basically a black box with some algorithm in it or some operation it performs based on some inputs and gives it in its output pins. It runs server side for performance, so you can have PyDPF core on your local machine, discuss with a DPF server in your HPC cluster, and you're going to run the operators and the workflows on the HPC cluster, let's say. They are mostly coded in C++, but we also provide, let's say, the possibility to code them in Python and to load them server side and to run them, still run them server side, even though you coded them locally in Python. That's the second presentation I wanted to make. So if I'm quick enough, maybe I'll put it in. The workflow, just boxes and arrows. Most people are familiar with it. The idea is to connect operators in very different manners. It doesn't have to be just a line like this. And you have workflow inputs and workflow outputs, which are not necessarily the same as the operator input pins and output pins. What's nice is that when you build a workflow, the user, the next user, you can save it basically and share it. And the next user doesn't have to know about the connections and the different logic within the workflow. You can just expose certain input pins as a global workflow input and expose certain outputs as a global workflow output. We're going to see that in just a few seconds. So how to create DPF workflows with PyDPF? You start with your basic imports at the top, and then you instantiate a new workflow, a new PyDPF workflow. And then in this example, I just wanted to show how you can basically feed in a result file. And the best way to do that is maybe those of you who already know PyDPF are familiar with data sources. And what you can get and build based on the data sources is a stream, what we call a stream container. And the nice thing with that is that it's going to handle a little bit of caching for you. So for example, if you're in your workflow, you request the same mesh multiple times in different operators, it's basically going to cache it and not recompute everything. So the overall workflow is a bit faster. Yeah, how do we, okay. I don't know if you can see my mouse, but basically I start by instantiating the streams provider operator here, and then I add it to the workflow, and then I say that basically the data sources input pin of the stream provider operator is going to be exposed as a workflow input called result file. And so that's what you see on the right. I have the blue box, which is the overall workflow. Then inside is a black box, which is an operator. And in this case, we have only one, which is a stream provider operator. This operator has one input pin, which is data sources, and one output pin, which is a streams container. So that's what it does. It gives you a streams container based on the data sources. And so I just exposed the data sources pin as the workflow output. That's why it's in blue and it's named result file. So, okay. Also, I generated this view using workflow.view. It's based on GraphViz. It's explained in the doc. You can check the API reference for the DPF workflow. It's all in there. Next, what I do, because just building a streams from a data source is not that interesting, I add a mesh provider. So what this operator does is it provides you the mesh based on whatever you give it as input, so a streams container or data sources, so basically a result file.
Paul, you have been mute.
Oh, okay, thanks.
Yeah, Paul, sorry.
No problem. I don't know where I was, but basically I instantiate a mesh provider here so that we have a workflow that is a bit more interesting. And so what I do is I directly connect to its stream container input pin, the stream container output pin of the previous operator. So that's from operator to operator. It's hidden within the workflow. Then I just add the operator to the workflow, and that's why when I do a new workflow.view, you can see it in the workflow view. All right, next step. I wanted to split this mesh based on given property. In this case, what I do is I instantiate a mesh splitter operator to which I give as input the property material. So here you can see that I have a string, which is basically an outside value, let's say, or a static value, which is fed into the property pin. And then I say that its mesh input is going to be the mesh output of the mesh provider. It's pretty basic, pretty logical. And then I just have to add the operator to the workflow. So you can see here it appearing on the right. Then what I can do is I can expose the meshes output pin of the split mesh operator as a global workflow output. So that's why it's in blue on the right and it's outside of the blue box, let's say. And what's going to happen is that if I share this workflow, so this blue box, it's basically going to be just this blue box available to the user with the result file input pin and the meshes output pin. You cannot really look at what's inside, or if you really want, maybe you can, but I mean, that's not the point. The point is that you share it this way. And now if I show how to use it, what I can do is define an input. So I have a result file. I define a data sources based on it. Then I feed these data sources to the result file input. So that's workflow.connect. I give the name of the input pin and then the object I want to connect to it. And then I can just ask the workflow to compute an output. So you can only ask for outputs that have been exposed. So in this case, for example, I ask for the meshes output pin. And I know I ask for it as a meshes container type. That's you have to request the type. And then when I print that, I see that I get a meshes container with two meshes defined on body and mat. For some reason, these two are linked, but basically I split the mesh based on material. There were two materials, and I now have two meshes. For those of you who are not familiar with what a meshes container is or mesh region is, I suggest you go look at the documentation for PyDPF core. It is all in there. Then I just wanted to show that I can also, of course, before sharing the workflow and while I'm constructing it, I can also set different outputs. For example, here I get the mesh output of the intermediate mesh provider operator. Even though it's not at the end of the workflow, I can still expose its own output as a workflow output. So if I'm interested in intermediate steps or intermediate outputs and stuff like that, so you can make your workflow a bit more observable, let's say. And you can see that I can get this output, and when I print it, I have the original full meshed region. All right, so to go further, I suggest to you again to go look at the doc. We have an operators page on the user guide section, and then we have the operator reference as the main section of the doc, which gives you the list of available operators and things like that. All right.
Thank you, Paul. What we're going to do is we'll give the stage to Oscar, and then we finish with you with the latest example. We are going to overrun. This is recorded, so the ones are very much welcome. But let's pass on Oscar and finish with you with the latest example, Paul, if you don't mind.
Okay, thank you. So let me take the ball. Can you see my screen?
Yes.
Okay, so I'm going to present the topic of creating custom results files through DPF. As I'm not going to go into details here, but DPF has capabilities to serialize DPF objects into several file formats, so CSV, VTK, and also HTF5. There are examples in the PyDPF documentation that explain how to use them to serialize DPF objects. But the idea here is to go a layer above that and provide capabilities to customers to go from current result files from our solvers, such as RST from EMEA to HDF5 files that can be filtered and compressed through DPF. So for doing that, we will use the operator called migrate to H5 DPF, and these operators provides capabilities to customers to apply HDF5 compression such as gzip, and also decide which are the results that the customer wants to export, filter them, and then compress them further. If I'm going one slide next, this is how the migration operator works. So we go from a data source that would be, in this example, an RST file, and we would apply filtering and compression workflows onto each of the results that the customer has selected to put in the result file. These filtering and compression workflows are workflows just as Paul explained in his presentation. They just need to be created in a specific way so that the migration operator can use it. But the idea is that the customer will connect to each of the results they want to export one filtering or compression workflow, and this result will be put in the result file. And this result file will also store, if a compression method has been applied, the decompression workflow, such as the customer will just need to call through a DPF operator for that specific result, as they would do if they called from an RST file. So in this case, if you look at structural temperature, which is BFE and MEPDL, the customer would apply a filtering and a compression method into it, and the decompression workflow will be stored in the result file so that they will be just using structural temperature operator to get it from the result file. An example of the filtering workflow, this is kind of the pattern for how to create them. These filtering workflows need to have two specific pins, so one called unfiltered input and one called filtered output. And an example for this would be a normalized high-pass filter. So we can imagine that you have stresses and you only want to export stresses up to a certain value. So you can say, for example, I just want to export the stresses that are above 10% of the threshold, which would allow you to compress the file a lot compared to the original RST file. The workflows that are currently available are stored in the Ansys install. In this link over here, we have 4 filtering workflows available and 2 compression workflows available. But the idea is that with these templates, customers could be creating their own compression and filtering workflows and then apply them into the export of the file. Just next, I'm going to quickly show an example. So this code here allows to read from an RST file. We are importing one of these workflows that I just showed that allows to pass input pins to the reader of the results. And we are applying a compression workflow into the displacement operator. So the migration operator, we decide that we are only exporting displacement and equivalent stress, and that we are applying these filtering and compression workflows into displacement and stresses. So the generated HDF5 file, if we look at the results, it will have the equivalent stress and then displacement information. And in order to read this result file, you would read it just as you would from the RST file. You can ask for result info and you would see the different results that are available, and then you can also plot them as you would do from the RST file. You just need to specify that the key of the file is H5 DPF. And just a last example, this method can be also used to compress original results files. So in this blade example, the original file made for 25 giga. So if we compress everything through gzip, we come into 12.8 giga. But if we filter it further, like only storing the skin of the elements and then compressing it through proportional decomposition, we can reach compression ratios that are much higher, up to 20 in this case. And yeah, that's all for me. I will pass the ball back to Paul.
Thank you. Paul, do you want to wrap up with the last presentation?
Yep, sure. Sorry about that. Let me. Okay. So yeah, I just wanted to also mention the fact that you can build your own custom DPF operators and plugins with PyDPF core, and you can share them in your company and reuse them. Very quick overview. Here I'm going to show how to create a custom operator which computes some statistics based on a field. And the goal here is to show that we can do it in Python using PyDPF core, and then we can send it server side and make it run server side. So on your, let's say, cluster machine or whatever. So here you can see that I created a file called easystatistics.py, and I did some imports. That's not very important, but basically I import stuff to be able to build custom operators, and then I create a class which is called easystatistics, and which is inherits from custom operator base. I basically give it a name, which is going to be easystatistics, and I defined another function outside of the class, which is called load operators, which is going to record when called, record the operator on the server side. That's not very important for you to know, but it's mandatory, so I had to mention it. You can do specifications for operators, so you can basically create your custom specification, give it a nice description for the user to see, and then define the input pins that it's going to have and the output pins that it's going to have, so with names and accepted types, basically. You can also give it properties. For example, here I give it a username and then a category. Whenever I generate my custom documentation, it's going to appear in the math category of operators. And then we have the run function, which we inherit from the custom operator base, but of course we override. And here what we do is we have a first step where we get the inputs. So in terms of input pins, we only have a field, which we can feed in as a field or as a fields container. So first I test if I have a field. If not, I test if I have a fields container. If so, I take the first field in the fields container. And if I have nothing, best practice is to raise errors when inputs are incorrect. And then I have the actual logic of the operator. So using NumPy, I can compute some statistics based on the fields data. So what's nice here, I'm showing that you can basically build your operators with a dependency on some other Python libraries. We will see next how to package that, but you can imagine including TensorFlow or whatever you want in your operator and use it in the logic for the operator. Then I just set some outputs as defined by the output pins, and I call set succeeded to know that the operator succeeded if I reach this line. And then how we can use the operator. So I made another script, which is this time a user script, let's say, the one I'm actually going to run. It's called custom operator use. I do some imports. Then I start a gRPC server for DPF because sadly the custom plugin and custom operator feature is not available when we are in process, but that's not such a big issue. And then what I do is that upload the file server side, and then I load it, calling dpf.load library, gives a path to the file, to the operator file, give the name, and then I say the name of the function to load the operator and record it. Once I have that, I can, again, in my user script, define some input here. So it's a displacement norm field. Then I can instantiate my new operator as so, calling it by name. Or if I regenerated the PyDPF core operators Python code, I'm not showing it how to do it, but you can do it. So you can do dpf.operators.math.easystatistics. It's doable. I can set its inputs, and then I can request the different outputs, and we can see that we print the different outputs that we generated through the operator. It's a bogus operator, but you can see it's working. And then I wanted to mention the fact that you can create your own whole plugins based on this feature, let's say, of creating custom operators. So if you have multiple operators, you can record and package them as a plugin. It looks like this. Basically, you can set requirements if you have dependency on other libraries. You can generate side packages automatically, which is going to be used server-side to include the different libraries you depend on. Then you have an init file, as you do in most Python plugins. And then I declare some operators in these different files. But what I wanted to show is contents of the operator loader. So basically just a record of an operator and then the init file, not very complicated. It's recorded so you can watch it later. And the XML file, which is important, I wanted to mention, which basically tells the server where to go reach for the side packages that it has to use to run the operator when you have Python library dependencies or third parties that are not in the default Python environment shipped with DPF. To use it, this custom plugin, you can do basically the same thing as for the custom operator, and you can even use a helper I made, which is load plugin on server, where you basically give the target to the plugin. It's going to load it on the server. It's going to load the different operators, and then you can basically access these operators on your server, just like if they were in a native plugin, let's say. All right, that's all I had to show. Thank you for the opportunity, David, and thank you, everyone.